Okay, howdy folks, I'm back. You know it. Another day where we're absent. So, I'll finish off chapter 3 and we'll look a little bit at the homework that kind of want you to work on for chapter 3. That's probably what we'll do today. Start by going to the PowerPoint. Okay, so where we're going to be from here is what's called the null cycles or do-nothing cycles. Not all chemistry that occurs in the atmosphere necessarily accomplishes anything. Sometimes chemistry serves as kind of a holding pattern, that the reaction will go, it will hold in this chemical, and then it'll go back, because a lot of chemicals cycles can be reversible at times. So we'll see some of these cycles. That it's not just the cycles we talked about, where ozone is made, ozone is decomposed, and there's catalytic ozone decomposition. So there are some that will make this a very complicated system. There's null and Holden cycles. Null, essentially, you remember zero cycles, zero sum. This will temporarily prevent species from taking part in catalysis. Null cycles are ones that result in no net odd oxygen removal. These cycles will compete with catalytic decomposition during the daytime. While ozone is decomposed, it can quickly reform. So the big thing, if we look back at the previous cycles, the idea is that we turning odd oxygen species into even oxygen species. Even oxygen species are not nearly as reactive as our odd oxygen species, ozone and monooxygen. So, for example, nitrogen monoxide, if it hits an ozone to form O2, okay, so that's the first part of our catalytic decomposition. But if instead NO2 gets struck with high intensity light before it hits a monooxygen, it can cleave off one of its oxygens to reform our NO catalyst. Now, so basically, it's the same as a normal ozone decomposition. Ozone gets struck by high intensity light and forms O2 and monooxygen. So this monooxygen isn't going to react with the NO, but it can react with the O2 to reform ozone. And it can react with NO2 to catalytically decompose. But the idea here is that we've taken off the second stage NO2 and we've gone from odd oxygen species to odd oxygen species in this two-step cycle, as opposed to the normal cycle, which was an ozone and a monooxygen go to two oxygens. Another such one, if NO2 hits an ozone, it can form NO3 radical. And then this NO3 radical isn't part of the catalytic cycle, gets struck by light to regenerate the NO2 and a monooxygen. Of course, this monooxygen could react with our NO2, but the net effect is, okay, if ozone is in high enough concentration, it's taking the NO2 out of the system for a while. So it's still the same net effect. The idea is that anytime we go from two odd species to even species, that hurts our ozone layer. But if we go from odd to odd, we're good. Now, a Holden cycle, we form a new species that, while the species is unable to catalyze any of the decomposition of ozone processes, it doesn't necessarily remove this from the atmosphere. So it just keeps it there trapped for a period of time. Now, after such period of time, eventually it will decompose back into the catalytic species. This can be both good and it can be bad. We can maybe try to trap it in this non-reactive form, but it could also allow these highly reactive species to travel, as we'll see in a bit. But so NO3 that we just saw could form in that null cycle can hit NO2 and a third ion, and it forms N2O5. This N2O5 is relatively stable. It's non-catalytic, and it's actually a reservoir storing between 5 and 10% of our NOx species at any given time. Now, there's two other such holding cycles that with 50% of the NOx and 70% of the chlorine. So, like, NO2 can bump into OH radical and form nitric acid, and chlorine can bump into methane to form HCl and methyl radicals. Now, this nitric acid stores the NOx or NOx at night, but nitric acid will photolize back into the NO2 in the daytime. So at nighttime, when we don't have the high intensity light, it basically stores this, and so it stops our decomposition in this way until day comes, and it does. HCl releases chlorine and water by reacting with hydroxyl radical. So HCl keeps it stored until it bumps into hydroxyl radical and then goes back. So once again, they kind of usually store these at nighttime and reform them in the daytime. Now, most of our ozone holes are actually centered around our Arctic and Antarctic circles. So these holding cycles that store this allow these molecules to travel a good distance. So such holding cycles will store the catalyst until they leak back into the troposphere, and allows this to be transported across the globe. So even though it may be formed near the equator, the mixing in the troposphere allows us to push this to the polar or polar regions. So, like, for example, chlorine monoxide, when it hits a hydroperoxide radical, forms hypochlorous acid in ozone. Or hyperperoxide radical hits NO2 and it forms nitrous, that would be pernitric acid, because it's a peroxy radical version of nitric acid. And ClO could bump into NO2 to form a chloronitrate. So basically these molecules get stored. They get frozen in this, and they're going to be heavier than air. They're going to sink back down from the stratosphere to the troposphere, and then the mixing pushes them to the Antarctic and Arctic poles. Now, a monitoring station in Antarctica discovered a noticeable decline in ozone levels in the early spring, which was September, the Antarctic spring, remember? So in the 1980s. Remember, the weather condition, the seasons are reversed on the South Pole. So, by 1984, this became evident this was a yearly event, which the maximum loss of ozone was in the September and October, in the spring moving on to the Antarctic summer. And then it builds back up over the Antarctic winter and keeps on cycling. Between 1956 and 1966, that ozone layer was about 314 Dobson units. In 2001 and 2003, the average was less than 150. And this ozone hole essentially extended 28 million kilometers squared, even as far as Chile and the Falkland Islands. Now, in the Antarctic and Arctic conditions exist where the seasonal and springtime and the ozone depletion event can occur. It's a result of climate factors and the accumulation of these reservoir species that are released at the onset of the first daylight of the polar spring. So they stay frozen up in these species. Suddenly it starts to warm up, and it causes these frozen crystals to melt, and they become reactive again. So during the winter, the intense cold and the Earth's rotation causes a giant vortex that draws all the air towards the South Pole and a little bit towards the North Pole. There's a very complicated system where it allows the formation of polar stratospheric clouds. So normally, clouds stay in the troposphere. So there's not a lot of clouds in the stratosphere. But it creates these polar stratospheric clouds that will either store the nitric acid and water or the chlorine nitrate species. So HCl plus the chlorine nitrate will eventually on the surface of these polar stratospheric clouds will decompose to chlorine gas and nitric acid, which can be zapped apart with light, or water in these chlorine nitrates forms hypochlorous acid and nitric acid, which can be zapped apart into HOX and our chlorine radicals. But these clouds remain stable until the polar spring and the onset of the sunlight in the late October. And so we start zapping apart our chlorine to our chlorine radicals, the hypochlorous acid into chlorine radicals, and the HOX radical, OH radical. Now, while these are sufficient to catalyze decomposition, due to the high concentration of chlorine radicals, we can have another set of reactions that can occur until the vortex actually breaks up, and then they are like stratospheric clouds. Polar stratospheric clouds will eventually dissipate in the late spring, which allows us to recapture the chlorine and allow the ozone to start building back up. Because we have so many chlorine radicals, it actually has these competing reactions. So chlorine normally would react with ozone to form chlorine monoxide radical. Now, if we have enough of that chlorine monoxide, we can form a dichloroperoxide. This dichloroperoxide can be zapped apart into a chlorine peroxide, and this can break apart into chlorine radicals. So it's a really complicated equation, but essentially it's the same as what it was. It's just we have some competing reactions that can slow things down and sometimes speed things up. This might be able to speed things up to some extent because we can avoid the need of the monooxygen. We can avoid the need for the monooxygen, which is usually in low dependence. So, while the ozone layer will undergo a similar situation in the Arctic, which occurs during March, which is the Arctic spring, but it doesn't happen to the same effect. We don't see the same strength of polar vortex pulling north as it does pull south. But it's colder and the polar vortex is stronger and more persistent in the south, yeah. But there are ways to remove these reservoir materials and thus kind of lower this ozone depletion event. Like we saw a volcanic eruption in the Philippines in 1991, which increased the amount of sulfate in the Arctic. This resulted in the following reaction where N2O5 and water binded to the sulfate aerosol to form nitric acid, which essentially rained out and got rid of that holding cycle N2O5, so it couldn't get to the Arctic Circle. And so we couldn't form these same clouds. And so what you can see right there is on this graph to the right, in 1995, we get this huge dip in ozone. But in 1992, the year after this volcanic eruption, the ozone layer is pretty robust. It's pretty thick. And we can see down in this graph to the left, we can see the trend of ozone thickness in the Antarctic Circle. So you see high in December, it starts to drop in November, drop to the lowest in October, then it starts to build back up, and it's kind of a wibbly wobbly back to January, and then it starts over its cycle. But that is the extent of which we'll look at the ozone chemistry, at least in the ozone chemistry in the stratosphere. Okay, so looking at some of the homework. Okay, so let's see. Okay. So I got a couple of these are easy, a couple of these might be a little bit trickier. Okay, draw a Lewis structure for ozone and dioxygen. And then using the data given below, qualitatively compare the bond enthalpies, bond orders, and bond lengths of these two compounds. So, remember, a Lewis structure should try to have, which should have all the valence electrons and try to achieve an octet when possible. Obviously, monooxygen will not have an octet. So you're looking at a bond enthalpies is how much energy is stored in the bonds when we break these bonds. So O2, you'll draw that when O2 species breaks into two monooxygens, you're looking at the energy of breaking the bond between the two oxygen molecules. We're looking at the energy forming the bond between a monooxygen and the dioxygen. So bond order is how many bonds are present between the atoms. Bond lengths looks at how long the bonds are predicted to be. So, now, it has been suggested that the loss of ozone is so I'll leave that one to you to work on. It's been suggested that the loss of ozone in the stratosphere could lead to a negative feedback that might allow more ozone to be produced. So, explain why such feedback is possible. Now, this self-healing does occur, but only to a small extent. So you're thinking about what happens when you lose ozone? What negative effect do we have that uses ozone? But of course, loss of ozone, that negative effect could in fact make more ozone. So this is a theory question. We're thinking about what does ozone block? High intensity light. If there's less ozone, what is getting through? And how could that cause more ozone to form? So it is a theory question. There will be a lot more theory questions because, hey, I don't want this to be a heavy math class if I can help it, but there will be math. I try to keep it as low math as I can, so I'm going to try to do as many theory questions as I can. A catalyst may be defined as a substance that enhances the rate of chemical reaction without being consumed in the process. By definition, a catalyst would have an infinite lifetime. Ozone decomposition catalysts, however, have finite lifetimes. So, what are the possible sinks for removal of the stratospheric catalysts NO and Cl radical? So, literally, what could potentially remove them? I mean, we talked about this. There's these null cycles, these do-nothing cycles, these holding cycles. What pulls them out of the catalytic cycle? And then what could helpfully remove them from the stratosphere? So once again, kind of a theory. Let's see, we have 5. Just want to make sure, yeah. Okay. So 11. The following proposal to repair the ozone layer has been made. Suggestion is to inject negative charges into the lower stratosphere, and these would then react with CFCs to produce harmless products. Instead of leaving them as neutral compounds, would make negative compounds that could break apart into chloride ions. From your knowledge of basic chemistry, indicate if this process would be theoretically possible and discuss the practical requirements of it. This one's a little bit trickier. But the idea is like, hey, we're just making everything negative. So we have chloride instead of... Okay, so let's see. Looking at that one. That one's, I want you to think about it, but... Oh yeah, I added some. Okay, so because I actually had a bunch more math-based ones, and these were kind of garbage. So, or at least way too difficult. So essentially, you're making chloride, or hydroxide, or hypochlorite. But so, I mean, you're thinking about even if you can make those things, what factors might make it difficult? So, for example, like, how easy is it to... I mean, in high concentrations, this is easy. But how much CFCs are actually there? Remember, catalytic amounts. Catalytic amounts. What does that mean? Is a catalyst usually in high quantities? Just think about that one. I said I can give you the actual answers that were given by the book later, but just think about these, and you don't have to be perfectly right. What are the main natural and anthropogenic sources of HOX, NOx, and ClOx radical species? Describe any connections between natural and anthropogenic sources of the various species. So it's just coming down to thinking about how these can be produced. You don't have to get them all, and we haven't talked about all of them yet. Let's see if you can get some of these. And then finally, 16, although the null or do-nothing cycle, it sounds in effect harmless. Describe the potentially harmful effects that are associated with these cycles. I mean, even though it doesn't necessarily deplete ozone permanently, it's not just doing nothing. So think about that and try to answer these questions. But okay, that's where I'm going to probably leave us. If we don't have class Friday, we'll talk about what we're going to do for lab, and I'll have to make another video, but for now, that's good enough.